Hello, I'll be presenting Team 22's study on the Sepsis 3 definition, how its changes to sepsis clinical criteria impact the performance of pre-existing sepsis and septic shock prediction models. Sepsis identification is a major challenge in healthcare because it's not a specific illness and there's no gold standard when screening for sepsis onset. The latest official definition published in 2016, a life-threatening organ dysfunction caused by a dysregulated host response to infection. For septic patients, mortality rate increases to 10% or more, and every year, more than 1 million are diagnosed just in the US. Our experiments target a 2012 study by Gosh, Ho, and Lee, which used multiple logistic regression models to predict sepsis and septic shock. This is our target study. The goals of our study are to apply the latest Sepsis 3 criteria to well-established sepsis and septic shock prediction techniques that predate February 2016, when Sepsis 3 was published, and then to observe the impact of Sepsis 3 on the model's performance. The Sepsis 3 criteria demands a computational approach to measuring organ dysfunction and identifying suspicion of infection. We wanted to leverage modern big data technology to process patient ICU data in the MIMIC3 database. Our analytics pipeline was constructed to follow a common big data architecture for machine learning algorithm development. We leveraged the power of processing and manipulating large data using Apache Spark analytics engine deployed in Microsoft Azure's cloud platform. For machine learning, Python libraries such as Pandas, NumPy, and scikit-learn were used. We initially analyzed sepsis-related data in MIMIC3. The flowchart shows how we construct the 4 cohort groups. The yellow box shows the process for identifying sepsis patients under Sepsis 1 and Sepsis 3. The red box shows how we identify septic shock cases. Please note that we are identifying Sepsis 1 patients using methods described in the target study, and then we filter out patients that do not meet Sepsis 3 criteria. All 4 prediction models are displayed at the bottom of the diagram and their performance will be compared. As for our algorithms, we are using imputation methods described in the target study to fill in missing values, and during training, a grid search cross-validation is performed to optimize the machine learning model parameters. These 2 flowcharts are intended to illustrate how this study benefits from Apache Spark's Spark SQL module. Each flowchart describes the process from raw MIMIC3 CSV files to the final datasets needed for developing all 4 prediction models. Notable phases of this pipeline are the red boxes, which apply multiple computing workers for join operations to the chart events table. And chart events is a 35 gigabyte CSV file that can take full advantage of the computing system's memory. Please note the section within the purple box, which is a memory-intensive calculation of the SOFA score, which was critical in precisely identifying Sepsis 3 septic patients. As described in the target paper, there are 2 sets of features considered, clinical history and physiological metrics. The observation window is the first 6 hours of ICU stay. This is where we extract feature data. The onset window we define as 6 hours after ICU check-in to 24 hours after. This is where we check for sepsis onset and Sepsis 3 patients. We use the SOFA score to measure organ dysfunction and administration of antibiotics to infer suspicion of infection. For sepsis prediction, as illustrated in the bar chart, controls made up approximately 90% of the patient cohort, so we balance the classes during training using class weighting. See the 4th column of the table. Our Sepsis 1 model, which attempts to use the same methods described in the target study, had slightly poorer performance. With our Sepsis 1 model serving as a baseline performance, the Sepsis 3 model performed slightly better. For septic shock prediction, looking at the same column, our Sepsis 1 model performance was also lower than the target study. However, the Sepsis 3 model demonstrated a 13% improvement over Sepsis 1. This table lists the results for the SVM and decision tree models. Please see our paper for more details. AUC was consistently greater than 0.74 for this low dimensionality feature set. The Sepsis 3 models were consistently better performance-wise. As illustrated in the ROC plot, sepsis prediction showed slight improvement, while septic shock showed a dramatic improvement over Sepsis 1 criteria. Pre-pause testing and model tuning were crucial for acceptable performance. Class weighting drastically improved our performance, and the imputation methods described in the target paper were helpful in retaining more septic cases in the train and test data. The target study did not provide a full explanation of some of the methods, so we made some assumptions. For example, the target study may or may not have used class balancing. Assuming they did, there are other approaches such as undersampling and oversampling as opposed to our study's balanced class weighting during model training. Our Spark cluster's parallelized processing of the MIMIC dataset enabled us to be extremely efficient during algorithm development. The logistic regression models perform better consistently when applying Sepsis 3 criteria. We applied hard metrics with regard to organ dysfunction and suspicion of infection, which may have reduced the number of misdiagnoses. We suggest the following improvements to future studies. Our onset window stopped 24 hours after ICU admission. We feel it would be beneficial to extend the window to the end of the ICU stay, which would be computationally more complex. Focus on removing humanly impossible outliers from physiological metrics. This could catch observations that introduce variance during training. And lastly, use clinical notes to mine for more information surrounding septic patients' physiological state. Thank you for your time. A link to our source code is in the video's description on YouTube.